Alright, so we're gonna be talking about unsupervised domain adaptation today. I, this is a situation where you have the training data, which is data and labels for one domain, and you do not have the labels for the other domain. You only have the data. For instance, this could be the case where you, let's say, train an object detection model, which is trained on data collected in New York, and maybe you want to run it on in Paris, or maybe you want to run it in Bangalore. Uh, so it won't work right off the bat. So you need to kind of adapt the domains, modify the latent vectors for it in order for it to work in different domains. So there are two ways to do it. Either you collect your data in, let's say, India, and then use domain adaptation, supervised domain adaptation. But let's say you don't have enough data, enough labels in your new target domain. So this is where unsupervised domain adaptation kicks in. So here you would not need the labels for India. You would only need the data. So I'm gonna cover two papers today, deep domain confusion and unsupervised domain adaptation using Backprop. And these two papers have been used quite a bit in a lot of literature since 2015, as like pieces that work together as a part of a larger architecture. So the first paper is deep domain confusion. So the core idea here is you have two networks, the two networks that share weights, and on one network you pass your labeled images, which is your source data, and on the other network you pass your unlabeled images, which is just your data, no labels at all. So the basic idea behind this paper is you pass these two types of data into your network, and based on the two different types of losses, one is a classification loss, one is a domain loss, your model will adversarially learn to do two things. The first thing is it will learn to classify the output class better. Let's say if you're talking about MNIST, then it will learn to classify the classes 1, 2, 3, 4, 5, and so on accurately. And the domain loss, on the other hand, will try to discriminate between the numbers from two domains. So let's say if you have two data sets, MNIST, and there's another data set called MNIST M. The difference is MNIST M is a colored um, data set which has multiple perturbations in the images. So same data, like same numbers from 0 to 9, but different domains. So in this case, this model will learn to accurately classify the output classes and at the same time learn to differentiate between the domains. So how it does that is because of this joint loss. So LCA, as you can see, is the normal cross entropy loss, and there's another factor added to it called the MMD, which is maximum mean discrepancy. So I'll talk about MMD in the next slide. So how this network will work is, let's say if you have a batch size of let's say 8, and so you'll pass 4 images from your source, which is labeled, and 4 images from the target, which is unlabeled, and you pass them through this convolutional layer. Then it goes through two fully connected layers, and then the authors have introduced a bottleneck dense layer called FC adapt. So the goal for this is to kind of present a bottleneck so that the network is forced to learn all the important discriminating features. So once you pass it through the FC adapt layer, it goes into two different losses. The labeled images only go to the classification loss, while a combination of labeled images and unlabeled images go to the domain loss. So you calculate both of these. So the domain loss is essentially the maximum mean discrepancy loss. So once you have that, you combine these and then you run backpropagation as usual.
So there's that regularization parameter lambda.
Yeah.
How would one choose that? I mean, is it should you're basically trying to discriminate? You're trying to force the loss to favor either the discrepancy or the classification loss, right? So do the authors of the paper comment on the choice of lambda? I mean, how important is it? How much is varying lambda by, say, a factor of 10? How much would that affect your ability to give, the unlabeled data the labels that you need?
Exactly. So lambda is not a constant here. They vary lambda based on the number of epochs completed. So it actually increases. So at epoch 0, lambda is 0. And as you do like 10 epochs, 20, 50 epochs, the value increases and therefore increases the weight of the domain classification that you want to introduce.
Got it. Okay.
So what is MMD? Maximum mean discrepancy is just a way to calculate the distance between two distributions. The mean.
No, that's fine. That's fine. I mean, that's clear. The formula is very clear over here. No, I was just curious about how important is the choice of lambda, is what, and I guess you answered that because you said that as you go on training over epochs, you increase your value of lambda. So initially you just want to do classification, and then as you continue the training, then more and more you have to decide how to label your unlabeled data, right? So
exactly. Yeah.
I guess that answers the question nicely. Thanks.
All right. So this is it. So the authors here had two choices for FC adapt layer. So one was where do you actually place it, and also before that, the architecture that these guys followed was from this paper in 2013 that was the ImageNet competition winner, Chrysalis. I can't pronounce that. So it's that paper which has 5 conv layers and then 3 fully connected layers on top of that. So they had a choice to make. What should be the number of neurons in FC adapt, and where should they actually place it? So they conducted a few experiments. So the first experiment that they conducted was for where should they actually place it. So they placed it before FC6, before FC7, and before FC8, and then they trained their model. So they observed that placing it at FC7 gave them the maximum test accuracy, and at the same time the MMD loss was at the minimum. So this kind of reinforced the hypothesis that MMD here is in fact a good choice for domain loss. And they repeated this similar test for the size of the fully connected layer. So this is a grid search with the increasing number of neurons, and they happened upon 512, which gave the maximum test accuracy, while it wasn't the least MMD score, but still very close. So this is one kind of paper, and this architecture, which contains two networks with shared weights, is pretty common, and there are modifications now on top of this that the more recent state of the art papers use, but the core idea remains. There's this another paper called Unsupervised Domain Adaptation using Backprop. So the goal here is you, instead of having two separate networks that share weight, you have one common base CNN network. This is the feature generator. So it's exactly the same. You will pass both your labeled images and your unlabeled images here. If your batch size is 8, let's say, so you pass 4 labeled images and 4 unlabeled images. So all of them go till here, and they generate a feature vector. Now this feature vector is passed into two different heads. One head is your domain classifier, the other is your the regular class classifier. They don't use MMD anywhere here. Both of these losses, LY and LD, are cross entropy losses. But then the question arises as to how they actually train for train to classify domains or separate domains. So what they do is once they calculate the domain loss, they multiply it with the negative lambda, all the returning gradients from here, and they concatenate it here, and then the backprop happens as usual. So this is the core idea here, that instead of minimizing the domain loss, they are maximizing the domain loss. And like in the previous paper, there's another lambda here, which is also scaled with respect to the number of epochs. And it's actually the weight which is applied to these gradients.
So, okay, so quick question. So I think this here the domain classifier is more or less like something like a adversarial loss, right? So
Exactly.
okay. I mean, there's a discriminator that classifies domain, and I think the goal of the model is to fool this domain classifier to believe that both the images labeled and label are coming from the same domain.
Same domain.
Right.
So this was it. Like, so these are the two core papers, which are very much used in a lot of domain adaptation papers, which I've read. So, like for instance, there's this object detection paper which came out in 2018, that uses RCNN and this particular block of GRL. So this layer is called as the gradient reversal layer, and it's this block is used a lot in a lot of other UDA papers.
So I have a question. So can we, this is a bit sort of maybe a little technical, but I don't think so. But can we go back to the slide where you show those two networks in the start? So the deep domain confusion, maximizing for domain invariance. Can we go back to that slide?
Oh yeah.
Right. So it's like the fifth slide, I think. So what exactly are XL, XS, and XT?
So XS is the input from your source. XT is the input from your target, and XL
What do you mean source and target? This is not clear.
all right. So source is where you have the data and labels, like images and labels, and target is where you only have the images.
So XS is your label data points.
Exactly.
So, okay, so let's say S is XS and YS, right? XS is the data points and YS is the labels, right?
Mm-hmm.
And let's say they're in Rn. XT is also a subset of Rn, correct?
No, XT is not a subset of. So XT is an entirely separate data set.
Yeah, but I mean, it's of the same dimension as XS, right? The data points in XT are the same size as XS.
Yeah, that's correct. Yeah.
Right? And so XS is just the point. So like a data set is classes is the points in the label, right? So is XS the form of some vector and a class, or an integer, or
it's a tensor. So let's say if you have a 28 cross 28 image.
Right. So it's the image itself, and you don't really care about the label itself is.
Yeah. So the formula here is not like the exact which they use to calculate it. It's more representative.
No, that's fine. I mean, the representation is important. So that's what I was trying to get a hold on. So what is XL then? XL is the label data and Y is the class, right? So
Yeah,
it's just a standard classification loss. So how are XS and XL different?
XS is your input, and XL is the label, is the true label attached to XS. XS is not the image comma label tuple.
It's just the image itself, right?
It's just the images, yeah.
So then why is Y the true label or not? Oh no, Y is the label that you want to assign to XT.
Yeah.
And XL is XS, the tuple XS cross Y, right? It's the set of points, the data points as well as the labels. Is that correct?
Correct. Yeah.
Okay, that's good. So now I get it. So XS is XL without labels.
Yeah. Exactly.
Right? Got it. Okay, so then what you're trying to do, as far as I can tell over here, is that these guys are trying to minimize the difference between basically you're trying to say that you want to minimize the data distribution, the distribution for which the data is drawn for, between the unlabeled data and the data for which you have the labels for, right?
Yeah.
So
Exactly.
you're saying they're drawn from separate distributions, but we kind of want to align them in such a way, assign labels in such a way such that the distributions are as close as possible.
Yeah.
Right?
So, yeah.
So you're using this minimum mean discrepancy kind of thing. Great, makes perfect sense. Now the only question is, did they try other measures of difference between distributions? Did they mention that in their discussion at all, or is that something that's left?
Yeah. So they did not mention any other losses which they might have used. So there are multiple papers actually. So there's another paper called Deep Coral. So Deep Coral also has this exact same architecture, but instead of using MMD here, they have come up with their own loss, which is known as the Coral loss. So that's another paper that I think came out in 2017 or 2016. So a lot of derivative papers use either of these architectures and add on maybe autoencoders or different loss functions.
No. See, that's the point I'm trying to make, right? So what is the loss function trying to do? There's two parts to it. One, you're trying to minimize the classification error on your label data, right?
Mm-hmm.
And the between the label data and your labels that you want to assign. The next is you're trying to minimize the difference between, you're trying to make the distributions as similar as possible, right? The distributions across which you have your classes, right? So you have a data distribution, right, that draws a point and a class, right? So XS and the associated label, so every little XS and some YS, right?
Mm-hmm.
Those labels are drawn from some distribution. That's the assumption we want to make, right? In all of machine learning.
Yeah.
Right. So the question then becomes, instead of using MMD, can you use other measures of difference or distance between distributions? Because ultimately this is like a norm, right? MMD of XS is like a norm. It's a measure of distance. It's a metric, right? So there are other metrics as well, like KL diversions, Wasserstein distance, Earth-Lewis distance, all kinds of things, right?
So technically you can use, but I haven't come across any papers that have used anything other than MMD.
Just pop open Google, you'll immediately find something like Wasserstein domain adaptation, KL domain adaptation. I'm sure of it. This is the question that I was wondering, is if they had discussed any of this, because I don't know, like this is not my area of expertise. I don't know domain adaptation. I don't know the field. I was just wondering, like, had they discussed the possibility of using other measures of distance between distributions? And why have they chosen this particular measure of distance? Did they discuss that at all, or is this like
No, they did not discuss using any other loss function other than MMD. I don't know why that is. Maybe they tried and it did not work as well as MMD. But this paper only like top MMD top.
Okay, and they didn't discuss why they chose MMD. Did they mention why they specifically chose this similarity measure, this norm?
They did not mention that, but then they later kind of proved using these two empirical tests. Uh, that MMD does, but they did not theoretically discuss why MMD.
Okay. Well, I mean, part of the reason is you don't need to explicitly know the distribution, so you can direct. So it's easier if you have data and you don't have to do the added step of kind of estimating a distribution or anything like that. So I guess maybe that's why you can just directly use data points and do it.
Yeah, maybe. Yeah.
But again, the reason I ask is because immediately if you search things like Wasserstein, just Google Wasserstein domain adaptation, something will immediately show up. right? So, I mean, again, this is recent work, but
Yeah, that makes sense. So I'll look up if there are any other loss functions or the distance metrics being used.
yeah. So the question is, I mean, like Jensen-Shannon divergences, KL divergences, all of these things are there. So I guess, yeah, let's see what this paper does. Where is this? CVPR paper, slice master sign discrepancy for unsupervised domain adaptation, right? This CVPR 2019, so very new paper. Okay, so this is a good area of research for you guys. Interesting.
Yeah.
Interesting. Okay, thanks. No, I was just wondering. I mean, I was just wondering if they discussed it. I guess since this stuff is only coming out now, then I guess it wouldn't have been a priority when that paper was published.
Yeah, this is a very, very old paper.
I mean, 5 years is not an old paper, really speaking. Thank it all, right? Trevor Darrell's group at Berkeley.
I'm not sure. Because I could only find this on archive.
Yeah, but I mean, it's the authors are Trevor Darrell's and their group. Okay, fine. So let's see what they say about MMD over here. Let's see if they mention that. The standard distribution distance metric. Okay, they haven't discussed it. Want to reference use of strings. Okay, fine. So basically, they say that MMD is standard, and they leave it at that. They don't discuss. They don't discuss anything beyond that.
Yeah.
About the choices of metrics between distributions. Okay, cool. Thanks. So, are there any other questions or?
Yeah. Do you guys have any other questions? So I think nobody has any more questions.
Okay, so I guess that is it.
Yeah.
So, Sabsachi, how do you want to do this moving forward? So, do we have an idea of who's next on the list? And
Maybe I can speak next week.